the solar short-term variability with AIA, solar flare, pulsations, waves, and oscillations. Thank you, Laura. Take it away.
Great, thanks, Ryan. Hopefully everyone can see my slides. So yeah, first of all, thanks to the organizers to have me here today to give this talk. I, again, am like Paolo, I'm a flare person, so I'm going to be biased. And really, AIA has kind of changed the game with looking at short-term variability in the solar corona and the chromosphere. And like, I mean, in a 20-minute talk, it's really challenging to kind of talk about all the really new insights that AIA has kind of given us. So I'm going to really focus on solar flare pulsations, waves, and oscillations, and all the different types of things we see in terms of oscillations that are generated from a solar flare. So even in this background movie, we can see a solar flare, and this kind of eruption of material causes wiggles and oscillations and all different types of pulsations in the solar corona. And AIA has really kind of helped us understand that. So similarly, a disclaimer, I apologize in advance for papers that are not referenced here. And I hope that maybe in the breakout room and in the Slack channel, if things aren't discussed or I've missed something, or kind of other papers that you think are really relevant, we should definitely kind of continue this discussion. So yeah, so just first of all, focusing on kind of a solar flare. A solar flare is kind of bound to excite oscillations and waves in the solar corona. If you think about it, you have a massive release of energy, which is then impulsively given to kind of the compressive and elastic media of like the plasma in the solar corona and the chromosphere. And we observed kind of these oscillations and pulsations in many different ways. One of the kind of, and they're kind of noted here, we have kind of quasi-periodic fast propagating waves, quasi-periodic pulsations, and essentially, like that movie I showed a moment ago, kind of nearby loop oscillations kind of that are driven by this impulsive energy release. So just kind of focusing on maybe this one first, MHD oscillations observed with AIA kind of warrants its own review talk, I think, for sure. And I'm kind of sad I can't keep going into this in more detail. But one thing that flares kind of do generate are kind of these transverse kink oscillations that we see in nearby loops, or kind of flare loops within the region. And these were first discovered by trace observations, but it's really with AIA, with the kind of high cadence and high spacer resolution and kind of full disk observations continuously, there's kind of bound to have lots and lots of observations of this. And here's just an example of kind of a flare. And if we take slits through these different loops and we look at the space-time plot, we can see these oscillations and waves. And this has kind of given us a lot of kind of opportunity to do coronal seismology to understand different types of kink modes that there are in the corona, both kind of these decaying kink modes that are caused by flare. And we've also now seen these like kind of non-decaying continuous kink modes. So I would refer to the readers to these papers here, which look at the statistical studies, and then also to review papers of MHD waves up here. So that'll be kind of most of the things that I'll be talking about in terms of that. Moving forward, what AIA has also shown us is these things called quasi-periodic fast propagating waves, which were first discovered by AIA. So if we look at kind of the running difference movies of 171, we can see these kind of wiggles and kind of disturbances that propagate away from kind of an eruption from a solar flare and a coronal mass ejection. And here is a movie of the running difference, and you can see after a flare, we have these propagating motions that emanate away from the flare, almost in a tunnel-like way. And I'll talk a little bit more about that later, but here are kind of some of the reference papers that I would refer you to go and read. But really the focus of this talk I'm going to talk about is quasi-periodic pulsations, because I think in terms of looking at solar flare energy release, I think maybe I'm again biased because it is what I study, but I think they're really, really interesting. I think we can gain an awful lot of information both about flare physics and plasma physics from their observations. So they've been kind of observed from flare emission for many, many years. They're seen as intensity variations as a function of time. And really back over 50 years ago was the first observation of Parkes and Winkler. And since then, it's really been in radio and X-ray observations associated with non-thermal accelerated particles that we see these pulsations. And here's a really nice example of the Seven Sisters flare from Cannes in 1983, where we see kind of like coexisting pulsations both in radio observations and in kind of non-thermal hard X-ray. And again, I referred you to this review by Nakarikov and Melnikov in 2009, which kind of talks about all those observations. But really in the last solar cycle, it's not just in the non-thermal emissions that we're seeing these pulsations. We really see them across the whole spectrum of flare energy release. From the foot points in hard X-ray down here, we see them now in the GOES derivative, so the thermal hot plasma, if we look at kind of these small scale pulsations. AIA has given us the opportunity to kind of pinpoint down where these pulsations are actually coming from in certain events. So this is looking at 1600 in the chromosphere and then in EUV. And then interestingly enough, we also see these pulsations in type 3 radio bursts in interplanetary space. So this is kind of suggesting that perhaps pulsations are related to the energy release process if you have electrons accelerated outwards and both downwards. So again, these pulsations that we're seeing from a flare, oscillations from a flare, really occur across the entire electromagnetic spectrum. And just some kind of key things, they are now identified both in the thermal and non-thermal flare emission, and that's really the last solar cycle. We've seen them in the thermal emission as well. This is some work that was done by Dalla, where if you detrend the light curves in the thermal emissions, we see these pulsations that extend not only in the impulsive phase, but extend late into the decay phase. They have periods of around 1 second to tens of minutes. So, I mean, it is really an umbrella term we are talking about when we look at QPPs. And we're still not really entirely sure of what causes them. The timescales that we see kind of overlap with predicted MHD wave and oscillations that we would expect in the solar corona, and that's a really nice kind of mechanism to produce these things, and then in that way we can do coronal seismology. But again, because they are so multi-wavelength, perhaps it is kind of a signature of this intermittent bursty reconnection or energy release. And we're interested in studying these from several different reasons. You can't have a solar flare model without being able to kind of explain these pulsations. They also have a really nice seismological possibility. So if we can understand what are causing these pulsations and oscillations in flare, we can relate the characteristics such as the period to kind of properties of the flare that we can't directly probe, such as the magnetic field, the reconnection timescale. It can also give us a probe for density and temperature. And even furthermore, pulsations are also observed on stellar flares and other active stars. And some work has kind of shown that they have similar characteristics. So if we can understand kind of pulsations and oscillations on our own sun and use kind of AIA observations to determine loop lengths and relate those to the pulsations, then maybe we can do seismology on kind of coronae of other stars. So moving on, we're talking about a multi-wavelength phenomenon. It really is AIA that has kind of like pioneered this idea of looking at like a multi-wavelength observations of solar flares, as Paolo has kind of mentioned. So there are so many studies that have really come up in the last several years looking at quasi-periodic pulsations. And this is just one case study of a very recent paper led by Brendan Clark at Dublin, where again, I'm showing these kind of like multi-wavelength pulsations from the foot point through the kind of hot plasma up into interplanetary space. And by using AIA imaging observations, this pulsations had a period of around, I think it was over 100 seconds. We have the cadence to be able to pinpoint where these pulsations are coming from. And for example, here, if we look at kind of the 171 angstrom channel, we can pinpoint that it's coming from kind of this flaring ribbon. And we can connect then where exactly these pulsations and intermittent reconnection is occurring and connect it both with the kind of flare plasma below and above. And again, I want to reference all of these papers. There's been an awful lot of work done comparing kind of AIA observations with radio observations, with hard X-ray observations, and really with iris observations too. We've seen kind of an awful lot of pulsations identified in chromospheric emission. And also going back to chromospheric emission, it's not just related to kind of this non-thermal particle acceleration. This is some work that was led by Ryan Milligan, which looked at kind of full disk observations in Lyman alpha and found this periods of around 3 minutes that were occurring both in the Lyman alpha observations, which you can see in the wavelength transform here, but they were also identified in the 1600 and 1700 channels of AIA in the flare ribbons. What's interesting, these 3-minute pulsations wasn't detected in hard X-ray observations. So it's really suggesting that what we're seeing is an impulse injection of energy into the chromosphere, and then the chromosphere is then dynamically responding to this impulse of energy release, a deposition at the acoustic kind of cutoff frequency. So it's known that if we look at 1600 and 1700 channels, we do have periods of around 3 minutes usually, and this injection of energy at these kind of flare ribbons is essentially enhancing that periodicity. And more work has been done now. Here I was referencing some recent papers that have looked at this in a little bit more detail, looking at both Lyman alpha and the 1600 and 1700 channels. And moving back to kind of oscillations in flares, we've seen this is work that Paolo referenced in his talk, looking at coronal implosions. And this is a really nice example of looking at all the different types of oscillations that occur in a flare. So we have this implosion going on, and then we see these like transverse kink oscillations. And if we look along the slit, we can see clearly these nice pulsations that are occurring in the flaring loops. And they change kind of period from kind of lower down to higher up. But what's interesting as well is if you look at kind of the hot channels, both with GOES and kind of if we look at kind of 131 in AIA, you're seeing these quasi-periodic pulsations of around 60 seconds. So this is interesting, like there is an awful lot of oscillations going on within this flaring loop or this flaring structure, and perhaps these are connected. You have this implosion essentially where you have contraction of loops, then because they have inertia, they're not going to go back to equilibrium, they're going to oscillate. And perhaps that is what we're seeing, that these quasi-periodic pulsations are essentially driven by these kind of like triggering pulsations or oscillations we see within the flaring loops. And they kind of refer to them, this was a model then developed further by Russell, which is looking at these coronal loop contraction oscillations, essentially just the response of the removal of magnetic energy from the corona caused by the solar flare, which is really nice. Now, statistical studies have been one of the key things we've seen of the past solar cycle, particularly when we started looking at these pulsations and seeing them also in the thermal observations. And an awful lot of statistical studies has been done looking at these sun as a star observations, both with GOES X-ray observations and with SDO Eve observations with ESP. So these are just referencing some statistical studies looking for these small scale pulsations. And this is some work that I did where we looked at all the X, M, and C class solar flares of the past solar cycle with GOES, and looked at kind of the period distribution of these pulsations that we detect. And we see that the period is around 10 to around 100 seconds, which kind of overlaps nicely with what AIA can actually give us. But the question then links, if we see these pulsations in all these different flares, how is it related to the spatial scale of the flare? And this is what we can do then with AIA and with SDO. We can kind of use these databases that Ryan talked about, such as the one developed by Masha, the ribbon DB, which looked at kind of the ribbon and active region properties for many solar flares, X and M class solar flares of the past solar cycle, and we can compare these periods. So what we found is when we related the periods of kind of the larger X and M class solar flares to these ribbon properties, what we actually find is that the period scales with the ribbon properties, both with the total flux, the total area, and interestingly with the total ribbon separation. So what that kind of is a proxy for is loop length. So what we're determining here is that perhaps longer loop lengths host longer periods, and this goes back to help constrain what mechanism might cause these pulsations. For example, with MHD oscillations, you might expect that the period would then scale with the loop length. Furthermore, as well as looking at these kind of small scale thermal pulsations I talked about before, again, in the past it was really focusing on impulsive phase, but what we're seeing now is that these pulsations last for a very, very long time into the decay phase. And this is an example, one of the most prominent examples of these decay phase pulsations, which happened in that September X8.2 solar flare, that we can see for several hours into the flare, there are the quasi-periodic pulsations that extend on. And these are observed both in GOES, and this is looking at the hot channel 131 angstrom over this field of view. We can see these pulsations extend. We find, like some other works, that the period actually grows as a function of time later into this decay phase, and perhaps again this is a signature of longer loop lengths in the longer stages of the flare, and we have longer pulsation periods, which is interesting. And the question then arises, what causes these pulsations? Is it a signature of continued energy release into the decay phase? Or is it perhaps kind of like later energy release that is then triggering further pulsations? Because here, if we look at these signatures, they look quite periodic. So maybe they have coherent periodicities in the later phases of the flare that's associated with MHD oscillations. Building on this is some really nice work that was done by CJU at NGIT, where they looked at microwave and hard X-ray pulsations and were able to relate them to bidirectional outflows that were identified in AIA. So this is looking at 131. This is a running difference movie. And if we look at the time distance plot, we can actually, they were actually able to determine bidirectional outflows in the reconnection region, which is quite low down in the solar corona. And what they were actually able to do was to determine that the arrival of these downflows actually coexisted with the kind of pulsations they see in the radio observations, in the non-thermal radio observations. So perhaps this is suggestive then that this continued energy release into the later phase of the flare are causing these decay phase pulsations and may help us understand kind of decay phase heating and things like that. Another really interesting work that we're going to focus on is very recent work that was looked at these SADs, or the super-arcade downflows. And this was a nice observation because it was on disk and had favorable geometry to be able to actually identify these SADs interacting with the flare loop top. And what they were able to do was determine that as these SADs, or these downward moving arcades, interacted, they were actually able to heat, they were able to identify where it was heating the kind of loop top regions. And even furthermore, they found that these interactions with the loop top was actually causing quasi-periodic pulsations in the temperature in those hotter channels. So again, this is another signature perhaps of these pulsations being caused by downflows and continued reconnection into the decay phase. However, again, we need to be careful because these periods here are much longer than the periods that we were talking about previously, but it's a nice observation and really nice kind of opportunity to further look at this in a modeling sense and both in an observational sense. Now, kind of going back and looking at these flare-associated quasi-periodic wave trains that were first detected by AIA, we can kind of see, as you said, as I showed before, they kind of propagate away from the flaring region. And again, this is another nice movie which shows this. They're associated with impulsive flare energy release, and there's so many papers that have looked at this, and I would really recommend people that are interested to further look at these studies. But what's interesting in terms of this probably host needs to have its own talk, but just in terms of looking at quasi-periodic pulsations, if we look at the characteristics of these kind of QFPs or quasi-periodic fast propagating waves, they have kind of similar periods to what we expect or what we observe in kind of the X-ray observations. So the question is then, do these pulsations or these wave trains, are they associated with quasi-periodic pulsations? And in some cases, it has been shown that they are. So this was a really nice study done by Liu, and it looks at, again, this quasi-periodic fast propagating wave. And if you look at if you take a time distance plot along one of these slits, we can see these kind of moving pulsations, and they really nicely match, in this case, both hard X-ray observations from RESI and also in the ribbon oscillation. So we're seeing kind of 3-minute periodicities there, which is really kind of showing that maybe there is a relation there. And furthermore, there has been work shown that these kind of quasi-periodic fast propagating waves are associated with radio bursts. So we've seen kind of radio bursts, if we're looking at kind of megahertz frequencies, seem to have kind of repetitive rates that are similar to what QFPs have been determined in some certain cases. And in this case here, they've actually looked at kind of this is the wave trains, or these QFPs, and they're able to match them to these nice little bursts that they see in the dynamic spectra. And for this case, they said that it was actually the QFPs that were then interacting with the leading edge of the CME, which was then emitting plasma frequency. And there's more work here by Kumar and Dmitry Glutov looking at these kind of pulsations and the connection between QPPs and QFPs. And to date, I really don't think we have a good idea of how these things are related, if they are related. Can they explain kind of the shorter period pulsations we're seeing? Are they generated by the same mechanism? And I think looking forward to the future, we really need to kind of do more kind of statistical studies of these. It's a challenging thing to do in a statistical sense, but I think it has an awful lot of kind of diagnostic opportunities there to do this type of work, and maybe AIA can really help us look at this in the future, both from a seismological point of view and both from a flaring point of view. And just kind of to summarize and to kind of point some things into the future, AI really has provided us with a wealth of observations of solar pulsations, waves, and oscillations from these QPPs, quasi-periodic pulsations in the solar flare emission, from these quasi-periodic fast propagating waves that we observe from many flares associated with eruptions. And again, the kind of ubiquitous nature of MHD oscillations in the solar corona. And I think even in the last several years, in the last 5 to 10 years, it really is a rapidly developing field, and there's still so much that can be done. And I kind of, if anybody's interested, there was a really interesting ISI Beijing workshop, and they have a website and there's some really nice talks and references, and they're coming out with some nice review papers now, looking at the observations of the past solar cycle, particularly with AIA, and what kind of new observations we have been able to kind of use, and what we really need to do next. In terms of what we know and what needs to be done, we still don't know what causes QPPs in solar flares. And we don't know what the relation is to QFPs. There have been some studies to show that they are related, but these are usually longer periods. And we really need to kind of have a unified way to understand them both together. I think some of the challenges lie in the fact that we seem to determine anything that has a kind of time variability associated with a flare, we call it a QPP. As I said at the start, these things can have periods from 1 second up to several tens of minutes. And that is just too broad, essentially, to classify these. For example, some periods have stationary components, so the period doesn't change in time. Others have non-stationary components, so that the period and the phase change in time, or the pulsations are more pseudo-random rather than periodic. However, the pulsations are still interesting, and they tell us an awful lot about solar flares. So I think as a community, we need to come together as a kind of classification system of trying to determine what are QPPs, and within QPPs, are there kind of like more stationary, non-stationary, impulsive decay and things like that. I think what's exciting is looking at kind of like near future forward modeling techniques that have been developed, and there's been some really nice work that has shown the application of forward modeling to compare models with actual observations. And this is a really nice paper, 2019, that looked at this and looking at pulsations and flares and how they were able to relate it to their model. Now, there are some challenges, of course, with AIA, however, as it's given us an awful lot of new observations and new things we can learn, we are kind of still limited by a cadence of 12 seconds. As I said, pulsations we've seen in other instruments such as radio observations can go down to sub-second. So we really can't identify pulsations and oscillations kind of below 24 seconds of the Nyquist frequency of the cadence. So that would be really nice looking forward to the future. Particularly when we're looking at sausage mode oscillations, because at the moment with AIA, we just can't do that with the period, with the cadence that we have. And furthermore, I mean, AIA wasn't developed to be kind of a flare-focused mission, and saturation effects are a huge problem when kind of looking at these hotter channels where they completely saturate during a flare. Now, I think we really don't know where these pulsations are coming from in some cases. In smaller flares, we can maybe identify, but it's the larger flares that we're quite interested in. And maybe some work can be done in the future. We're looking at desaturation. I know a lot of work has been going on at the moment. So I'll finish there. Just want to say AI has given us an awful lot, and I really hope we can continue this discussion into the breakout room. So thank you.
Thank you very much, Laura, for a fascinating overview of a relatively new and exciting topic. Again, remind people just to please post your questions in the chat if you have any now, and or hold them till the breakout rooms later on. I can also see a lot of discussion going on in the Slack channel as well. Georgios, would maybe time for one quick question before we move on?
Sounds good. We have Hugh Hudson asking one question here. How are the Liu et al. Wave trains related to the monotone wave type 2 burst disturbance?
I actually don't know, to be honest. Sorry, yeah. Maybe somebody else on the call can discuss that further, but I'm actually not too sure myself.
Do you want to move on to one more from the one from Katie there?
Yeah, let's do that. Have there been estimations of the amount of energy that gets deposited into the oscillations? I'm thinking in terms of the full energy budget of a flare.
Yeah, so I think actually with I think it was actually with that implosion work that I showed with Paolo's observations, and I think it was on the order of 1% went into the kind of like eigenmode oscillations that you would see in these thermal pulsations. But I think an awful lot more work can be done in that, in a sense of trying to determine the energy budget. If we think of kind of hard X-ray pulsations where the modulation depth can almost go the whole way back down, I mean, that is almost the entire budget of the accelerated injection of electrons. But as far as I'm aware, I don't think anybody has really looked at that in detail, and I think it's an interesting thing to do for sure.
Okay, thank you again, Laura. And just while we move on to the next